Hello and welcome to the 8th video in this series on random number generators that accompanies the book Random Number Generators Principles and Practices. And this is the second series on entropy extractors. The last time we looked at the definition of entropy and the definition of an entropy extractor as something which takes some partially entropic input and outputs less data, but with a higher density of entropy. So higher entropy, but less total entropy overall. So in this video, we're looking at trivial extractors, and most principally the exclusive OR gate, and seeing how that can improve entropy. And it's the underlying operation that is used in all extractors, as we'll see. We have here, well, we're looking at the definition of entropy rate now, just because we'll be using it. We've talked about it a bit before, but we've got an example here of a non-uniform distribution. We have 4 symbols, 0, 0, 0, 1, 1, 0, and 1, 1. And our source is outputting only 3 of them with equal probability. So the probability of getting each of these symbols is 1/3, but the probability of getting a 0 is a 0, 0 is 0. It's not going to happen. And so the probability of a 0, 1 is 1/3, of a 1, 0 is 1/3, and a 1, 1 is 1/3, and a 0, 0 is 0. And using our definition for min entropy, what is the most likely symbol? Well, they're all equally probable, so we've got our maximum probability of 1/3. So negative log 2 of 1/3 is 1.58. The entropy rate is the amount of entropy out per bit. And each time we get one of these symbols with 1.58496 bits of entropy, we're getting 2 bits. So we divide it by the number of bits and we get 0.79248, or about 79% entropy in this source with a hole in its distribution. So it's not a full entropy source. It's not got a uniform distribution, and so it's not got full entropy. So we can now look at the XOR gate. This is standard electrical circuit and a mathematical operation, and it says if the inputs are the same, output a 0. If the inputs are different, output a 1. We have in electronics AND gates and OR gates, and well, several other gates, but those are the basic ones, and a NOT gate for inverting. And if you look at an AND gate, you get in this table where the inputs are 0, 0, 0, 1, 1, 0, or 1, 1, you will get out 3 zeros and a 1. If you have an OR gate, you will get out 1, 0, and 3 1s. So if I put random data into the inputs of an AND gate or an OR gate, I'd get biased output. But the XOR gate is different because the zeros and 1s in the output are balanced across the input symbols to 2 zeros and 2 1s. This tells us that there's some better properties with regards to extraction, and we can look at that. So let's say we have data coming into this where they are both independent of each other statistically, but the bias on the inputs is 1/3. So the probability of getting a 1 is 1/3. The probability of getting a 0 is 2/3. So it's biased on the low side. And that's coming in on both inputs. Not the same data, different data, but with that distribution. 2/3 and 1/3. If we look at the outputs, the probability of getting a 0 and a 0 on the input is 2/3 times 2/3, and that gives us a 0 on the output. And also the probability of getting a 1 and a 1 is 1/3 times a 1/3, and that gives us a 0. And similarly for the 0, 1 and 1, 0 case, that gives us a 1, we get 2/3 times 1/3 and 1/3 times 2/3, which are the probabilities of getting those bits on the inputs. And to compute the probability of getting a 1 on the output, we add up these two values, because those are the two values that lead to us getting a a 1 on the output. And to compute the probability of getting a 0 on the output, we add up this value and this value. And so there's the equation, and we find the probability of getting a 1 is 4/9, and the probability of getting a 0 is 5/9. We can observe that 5/9 is the more likely event, so 0 is more likely to happen than 1, but 4/9 and 5/9 both are closer to 0.5, the ideal, than 1/3. So while the total entropy out is less than the entropy in, because we've got 2 lots of it coming in for each output, the entropy rate, the entropy per bit, is higher. So we'll look at that in a little more detail. We've got the input entropy rate of negative log 2 of 2/3 because we have 2 possible inputs, a 0 or a 1 on each pin, and they have probabilities of 2/3 and 1/3. So 2/3 is the maximum likely symbol for a 0, and so that's the one we plug in, because the definition of min entropy is negative log 2 of the most likely symbol, and we get a value of 0.585 bits of entropy into that pin, and into both pins. In fact, at the output, we've got 5/9 is the most likely. We have 4/9 for a, which was it? It was 4/9 for a 1 and 5/9 for a 0. So a 0 is the more likely symbol, and we compute the entropy, and it's 0.848, and we can see it's higher. The entropy per bit is higher than the entropy per bit on an input pin, but it's not higher than the total entropy in, because we've got 2 pins, 2 lots of 0.585. We divide that by the output entropy, and we get 1.38. And if so that's how much data how much entropy we're putting in per bit of entropy out. And if you invert that, you find out that we're 72.5% efficient, in that the entropy out is 72.5% of the total entropy in. So there's less entropy coming out, but since there's half as much data coming out, because there's 2 inputs and 1 output, we're getting a higher entropy rate. We can define the probability of a 0 as we did in the previous slides, getting the first input as a 0 and the second one as a 0, or the first input as a 1 and the second input as a 1, and the probability that is a 1 is the probability that the inputs are different, 0, 1 or 1, 0. That should be 1, 0 there. So we'll plug that into equations and do some rearranging, and we get 2 times the probability of a 1 minus the probability of 1 squared is the probability of the output being 1. This is a handy equation because the probability of a 1 is the same as the bias. The bias is a probability of getting a 1 in binary data. So we've got an equation here that defines the output bias of an exclusive OR gate as a function of the input bias. If we draw this graphically with the input bias of that to an XOR gate, or to each pin of the XOR gate, and so we've got this line of what we would get out if we were just looking at the pin, and the red line represents the output of the XOR gate, and given the input bias on the x-axis. The 0.5 line here on the output, the y-axis is the output entropy. The 0.5 line is the perfect goal, right? If we have our bias at 0.5, then we have full entropy. And we can see at every point, except at the full entropy point and the 0 entropy point, the red line is closer to the black line than the blue line. So we can see for all the possible input biases, which are neither full entropy or 0 entropy, the output of the XOR gate is better than better in the sense that it's closer to 0.5 than the input bias. We can prove that in a more general case of having any bias on the inputs. a different bias on the input. So pin A might have 0.8 bias and pin B might have 0.6 bias. And what we're going to show is that the output bias is better than the bias on the better input. So 0.6 would be better, and the output bias would be closer to 0.5 than 0.6 is. So we start off with our familiar equation. The probability of getting a 1 is that the inputs are different, or the probability that the inputs are different. And we're going to label the probability of the pin A being 1 with X, and the probability of pin B being 1 being Y, just to make the equations a bit less unwieldy. We're using this circle with a cross in it to represent the XOR symbol in mathematical equations. That's a normal thing to do. And so we can recast it like this, rearrange it, and we get X plus Y plus 2XY, which is the output bias given the input biases on the two pins, the output bias from an XOR gate. We'll also define the deficiency of the bias to be the distance from 0.5. So if I've got bias of 0.6, the distance from 0.5 would be 0.1. And so it's the absolute value of bias minus 0.5. So we want to show that the deficiency of the output, X plus Y minus 2XY, the output bias, is less than the deficiency of the input bias, X. Now that's only one of the pins, but if we can prove this, it's sufficient to show that this deficiency is better than the deficiency of the Y input, because you can just swap the labels and everything still holds. So we just have to prove it for one pin, and we've proven it for the other. And so if we plug that into the unroll this equation for the deficiency, we get the absolute value of X plus Y minus 2XY minus 0.5 is less than the absolute value of X minus 0.5. And that's what we want to show. So we're going to do the opposite and show by contradiction. So if we say that X plus Y minus 2XY minus 0.5 is greater than X minus 0.5, and the absolute value thereof, then we can say that we can just rearrange it to say X plus Y minus 2XY minus 0.5 is minus the absolute value of X minus 0.5 is greater than 0. But we can plug in X and Y. X and Y go from 0 to 1, their biases, and if we plug in the midpoint, 0.5 and 0.5, we get X plus Y minus 2XY minus 0.5 minus X minus 0.5, the absolute values. What we get is 0 minus 0 is equal to 0. So that equals to 0 is a contradiction with this equation we started with, our assumed equation that X plus Y minus 2XY minus 0.5 minus X minus 0.5 is greater than 0. We can show a case where it isn't. So this statement is not true. So the true statement is the reverse, which is that this is less than or equal to, or rather this is less than or equal to this. So we've proven that the deficiency at the output is less than or equal to the deficiency at the input pin, and for both pins. So that's nice. We were looking originally at the bias being the same on both pins, but it doesn't matter. The bias can be different on both pins. If one of the inputs has full entropy, if one of the inputs is 0.5 and the inputs are independent, then the output will be bias will be 0.5 because it can't get any better than that. But any bit of bias on either input will improve at the output. So what we've concluded here is, given independent inputs to an XOR gate with some bias, the output bias is always as close as or closer to either the input than either input is 2.5. So the bias gets better, but only for independent inputs. And if the inputs are correlated, it doesn't work so well, and we'll show that. So here is a command line for generating 1 megabyte of biased data with a bias of 0.35 and a megabyte of biased data with a bias of 0.25, and we've put these in some files, and we've just looked at the first 2 lines in these files as hex characters, and we can see what they look like. And you can see there's a preponderance of values with 1-bit set or 0-bit set. So there's zeros. 2 and 4 have 1-bit set, 5 has 2-bit set, 8 has 1, 9 has 2. There are not any with, oh, there is one here with 4-bit set, but only, I think that only appears one time in these 2 lines. So this is because the data is biased, and more so here, it is more biased. It's down at 0.25 instead of 0.35 in the other file. We'll then XOR those 2 files together bitwise. So I wrote a program called XOR Files, which takes in 2 inputs and outputs a file of the same size, which is the XOR of the 2 files. And then we run it through gent to see what the mean is. And the mean is now 0.425. And so what we're inputting is 0.35 and 0.25. But we XOR'd it and we got a single file with where the bias is closer to the to 0.5. But if we think about what happens when we have correlated inputs, let's say we had full correlation. So the bias is 1. Or sorry, the correlation is 1. So the probability that the 2 bits are the same is 100%. So you always get a 0, 0 or 1, 1, and then the output is going to be always a 0. And if the correlation is negative, fully negative, -1, then you always get different inputs, so 0, 1 or 1, 0. So the output is always 1. Obviously the bias is now as bad as it can be. The bias is 0 here and 1 here. It's as far away from 0.5 as it can be. And this is partially true for partial correlation. So let's try that. We'll make 2 correlated files. So I spent today writing a program called make correlated files. We produce 1K of data, and we're setting a correlation of -0.25 between the files. These are the 2 files that are generated. So each file itself is unbiased. So we measure it, and I've grepped out the mean line, and we find the mean in the first file is 0.501222, and the mean in the other file is 0.502444. And this is random data. It's coming from dev urandom, from the operating system random service. And both files have, or if you were to look at the files individually, they'd both look fully random. But we've XOR'd those 2 files together to get a file post_cfile.bin, and we look at the mean in that file, and we find the mean has got worse. It's 0.624389. So these 2 files are correlated. cfile1 and cfile2 are both correlated with each other, even though individually they look fully random. Together, they're not so random, because you can use one file to predict the contents of the other better than chance. And so this is an example of putting correlated data into the XOR gate and getting worse bias out than you put in. And so this is a general principle that correlation is a problem going into exclusive OR gates, and you have to do something else in order to extract the entropy from it. We can do XORing multiple bits at a time, and so we have here this non-uniform distribution we looked at before, and we're doing it twice, right? We're taking both symbols and we're XORing them together in a bitwise way. So 0, 0 XORed with 0, 0 gives you 0, 0. 0, 0 XORed with 0, 1 gives you a 0, 1, and so on. So it's the 2-bit exclusive OR. and or bitwise, where we're exclusive ORing the 0 and the 0 together, and the 0 and the 0, 1 to give us the 0, 0 and the 0, 1. So we plug in the probabilities. The probability of getting 0, 0 is 0, because here we see in the distribution we never get a 0, 0. So the probability of getting these patterns out from these inputs is 0. It's not going to happen. But we have other patterns which do. And so let's see, 0, anything that doesn't have a 0, 0 in it has got some probability of happening. And we've got those probabilities of a third. And so the probability of both of those happening and getting this output 0, 0 from that is a ninth. And if we add up all the probabilities of all the outputs, that all the combinations that give us a 0, 0, that's here 1/9 and 1/9 and 1/9, we get 3/9. And similarly for 0, 1, 1, 0, and 1, 1, we get 2/9 each. So let's see, looking at 1, 1, we have a 1, 1 here with a 9th. We have a 1, 1 here with a 9th. But the 1, 1 here is the 0, and the 1, 1 here is the 0. So there's only 2/9 here. So now we've got a distribution with a third here, and then 2/9, 2/9, 2/9. So the distance between the two possible values is now closer to 0.5 than, closer to each other than they were before. There was a full third difference, but now it's changed. They're closer, and we can actually iterate this multiple times. I'm going to take here we're taking two symbols A, B, but so here's taking just the one symbol, and we've got the original distribution of a third and 0. But we iterate it to get the probability of a 0, 0 and the probability of the other input, and we see that as we saw, the probabilities crossed, and then it crosses back and it crosses back, but they are converging on one quarter, 0.25, which is what we'd expect for 4 uniform inputs, or 4 uniform symbols, each of them probability of a quarter. So as you put more exclusive OR together, more bit pairs, you find that it gets closer to uniform. And we're doing quite a few here before it looks close to uniform. Maybe 8. You can't see the difference anymore. 8 pairs of bits. We can do the same trick on normal size numbers like 64 bits, which is what we get in today's 64-bit computers. And here, this is iterating together, or exclusive ORing together, two 64-bit values. And these values are taken from the read-rand instruction on an Intel CPU. And one of the things that the read-rand instruction does, it returns a 64-bit random number, but it never returns a 0. And I'll go into the reasons why in a later video. But you don't get the version. You don't get the value 0. That's not a big problem, because the probability of getting a 0 is 1 in 2 to the minus 64 anyway. That rarely happens. You'd have to look at a lot of data to notice that the zeros were missing. But let's say we didn't want that to be the case, and we exclusive ORed together 2 of those values in the hope that that would bring it closer to uniformity. So we get the probability of, this is computed using 200-digit precision using a Python NPF library. We see that the probability of a 0 is something 5.4 times 10 to the minus 20. The probability of the other value is 5.4 times 10 to the minus 20 after the first exclusive OR. And the difference is 2.9 times 10 to the minus 39. So that's the difference in the two probabilities. We exclusive OR in another of these values, and it now the distance is now less, minus 1 times 10 to the minus 58. Do it again. We should really take the absolute difference, so 1.5 times 10 to the minus 8 for the distance. And do it again, 4 values together. So this is 2, 3, 4. It's 10 to the minus 78. And here, on the fourth iteration, the difference is 0. And what this is saying is the difference has stretched out to more than 200 digits of precision. So these two values are the same out to 200 digits, which is plenty good enough for the purposes of cryptography. So if I were to take 4 values and, it's 2, 3, 4, 5 values rather, and exclusive all of them together from read-rand, I would get back to a fully uniform distribution for all practical purposes. And that's a pretty cheap operation. Read-rand is a pretty cheap operation in the computer. XOR is a cheap operation, so you can just go read-rand XOR, and 5 times, and you have this uniformity back that you don't from the source. Now that's true for most Intel CPUs, that you don't get a 0, but some of the system on a chip low power versions transfer the data from the random number generator 32 bits at a time, and then what you don't get is a 32-bit 0 value, but it's actually fetching 64 bits and returning 32 of it. So you're going to have the possibility of a 0, 0 or a pair of 2 32 zeros happening, because you got the 64-bit value with internally with the top 32 bits occupied and the bottom 32 zeros, say, and you get 2 of those. That's 4 billion times more likely than getting a full 64 bits of 0, 0 happening. So some of the read-rands actually give you that some of that uniformity back. If we move on to the that's it. That's the end of the talk. So we've looked at the XOR gate and seen that it is something that improves entropy relative to the input. We've proven that here that the output bias is always better than the better bias of the 2 inputs, even when those inputs have different bias. And then we've looked at examples of the bias the output bias being better when we just give it biased inputs that are not correlated, but when we give it correlated data where the values on the pins are in some way correlated, the entropy gets worse. Now a tiny bit of correlation, it still works, but any significant correlation, here we had negative 0.25, so a quarter, it got significantly worse. So correlation is something you want to avoid, and we can take steps to avoid that correlation, which we'll look at later. And we can do it multiple bits at a time, and we see how it improves the more times you XOR values together. And we saw that with larger values, like 64-bit values, it happens very quickly in a short number of steps. So I think that's as much as we want to do in this video. I was hoping to get to whitener algorithms, but this one's already getting pretty long. So I'll stop it there, and we'll look at whiteners in another video. So thank you and goodbye.